Good morning, everybody. Welcome to class. Welcome to this Monday, and we'll start soon. We're going to start a new topic this week. It's certainly going to take us all of this week, and we will borrow some of next week to continue with this. And the topic is classification. So we have completed one major topic, one major class of problems in machine learning, regression. We have 3 lectures and the lab session. And so we are going to have a larger and a bigger set of problems in classification. And that is what we will start today. I hope you have had a good weekend. I hope you have had a walk in the place I asked you. I said I will ask you, but that's not going to be a warm-up question for the day. A warm-up question for the day is actually related with the topic we're going to discuss, and it is related with the picture you see on the right. And it will be clear when we start discussing a little bit inside. Today's warm-up question, the honor of writing it will go to Wen Lee. I'm sure I'm pronouncing that name correctly. You're going to write the warm-up question for the day. And this is the question. What is your favorite sport to watch? Sport or game to watch, not to play. We probably have something that we like to play and something else that we want to watch. Tonight, maybe some of you will be watching the football game, a big game is happening. Tell me what your favorite sport to watch is. One of them is displayed on the right, as you see on your screen. If you have any questions, like we always do, you can unmute yourself and ask me or put them on the chat after people are done telling me their favorite sport to watch, because now it's very, very busy. But later on, when we start discussing, if you have questions, you can put that in chat. I will try to monitor, but you should always feel free to unmute yourself and ask me a question. Let me go ahead and get started with what we want to do today. And I'm going to try to use as much of the time as we have for getting to cover as many things as possible. And because this is a bigger problem or a bigger class of things to look into compared to regression, we will use every single lecture, all 50 minutes. Just as a note, the slides are posted. If you wanted to follow along on Blackboard, we don't need Chris today. It's there, and we've got the PDF versions of them, and I'm going to be running the PowerPoint version here. So if I need to stop somewhere and so on, I can do that. But this lecture, today's lecture at least, is based on a chapter from the book we started off talking about last set of lectures on linear regression, and that book is the book on statistical learning with applications in R, and this discussion on classifications is in chapter 4. I will be using some other source or some my own thing whenever I need to. For example, what will happen after today's lecture will come from somewhere else, but most of the things that we want to discuss, at least for a couple of the lectures, will be drawn from this chapter, including today's discussion. So classification, one easy way, by now everybody should be able to tell this, compared to regression problem where your response was a quantitative variable, a y, that would take some value. Here we are going to have a response variable that takes qualitative, or in other words, one of a possible set of discrete values, and that's why it's called classification. For example, if we were ever to care about classifying this class, people based on the color of their eye. Some people have brown, some people have blue, some people have green. I can't see now on screen how many people have green eyes and blue eyes, unfortunately, but we can classify people that way. This is not one of the biggest problems to solve in machine learning. It is not, but it is one example. The email problem is a big one that classify a problem, an email, whether it is spam or legit, and people have grown to call them ham, spam or ham. And this could be a major thing. And most commercial things that we have now, including your own mail browsers or mail client on your computer, has an ability to do that. And it's a big industry. And you would be able to do this by the end of this course, for example, or you can take a larger version of this where you have to classify documents like you will do in your assignment 5, and this is a classification problem. You can continue to have very many examples where classification is needed. And as I have repeatedly say it now, most of machine learning problems are actually classification problems. Think about what a medical doctor would want to do after they look at an X-ray, whether the patient is healthy or sick, or you've got some specimen that you've taken and then you wanted to see if there are enough indicators to classify people as one of several stages of some disease, or you've got my favorite example where you're hired as a consultant, this time not to do this advertisement thing on TV and radio and newspaper, but rather if you were hired to for a bank or an insurance company and they want to tell you to tell them when they see something, whether a claim that somebody has given is legitimate or fraudulent, and so you may classify them. You can continue in this way: image processing, vision, artificial intelligence. Very many of them are of the type for classification, and the algorithms we have and the kind of additional things, fanciful things we could do are there in classification. So one way to formally say this would be you're given a feature vector X and a qualitative response Y, and that could take some values in a set C, and that C is now a big kind of fancy C that you can see. The classification task is to build a function, just like when you were doing in prediction, you were building a function that will take this feature X, and then it's going to return one of these values of that fancy C. And it will give me an output, and that output will be one discrete value. That will be the way to formally state what a classification problem is. Wenli, for those who have come later on, you can type the warm-up question just one more time, not now, but a little bit later. And the question is, what is your favorite game to watch? When we do classification, most of the time, and those of you who have had some exposure to machine learning probably already know it, there is an even more important thing that is associated with the classification. Rather than just saying whether this thing is this or that or this, you had that picture in the classification, whether you had something to put in a bin, and whether it is in the recycling bin or one of these other ones. That's easy. We can think of it. But when it is more like the fraudulent document for a claim, what you really want to say is you would like to come up with a way to say this object belongs to this class with this probability. So the probabilities are more important. So if I stay for a second with that example of an insurance company trying to determine whether a document is legitimate or fraudulent, they would want your algorithm, your method would say, this document, having seen their IP address, having seen the person's history, their browsing documents, and whatever they have had interacted with us before, whatever they are saying now is fraudulent with a probability 0.9. And then some other thing you may analyze and find out it is 0.98. And then the company would then be interested in investigating, putting in resource, whatever it is that they have to do for the one that you thought was fraudulent with a higher probability. And so that probability becomes important. In fact, you will learn that this is actually how the algorithms would also work. The classification algorithms, they would never know for sure when it is an image classification problem, cat and dog. You would say, here is a cat with probability 0.9, 0.8 with probability 0.6, it's a dog. And so your algorithm would eventually rank these things and then give us an answer, the one that has the highest probability. This is the inner working of the classification method itself. But if you were to actually use, not just getting the answer, but actually use that probability to do some further decision making, then it is a very helpful information, because now you can allocate resources, as I just told you, whether an assessment of a document has an automated version of it has said this is fraudulent with 0.95 and 0.9. Both of them are really good, probably high probabilities for you to classify them as fraudulent. That's fine, but you probably don't have the resources to always investigate these things. So you want to prioritize the ones that have the higher probability. So the more important, more interesting question is usually to associate a probability with this function that is going to take a vector X and is going to return a discrete value, one of many C. And so that probability is important. Well, I have saved this example without having to display it. You have on, when you are following me along now on Blackboard, the PDF version of it, which displays every single one of these bullets, one completely in one. So you probably have seen this already. Let me take a moment and try to explain with one concrete example. This concrete example is taken from the book, and this is about a credit card. We have encountered this example before, and we will see today. We will see a little bit of more of it today. The way we encountered it when we were talking about regression was to see how we can handle variables that are qualitative. So we've got predictors, and some of these predictors have quantitative values associated with them, which makes it a natural thing for linear regression to do. But then some of them could be qualitative, and we saw how we can turn them into dummy variables and things like that. So in that context, we saw this credit card example. So I'm going to pick one thing there, just one thing, and it's going to be, or a pair of things. It's going to be income, the card holder's income, and the balance that they have on their card. And so this is a scatter plot. What you see on the left is a scatter plot. The only thing that has been done now compared to what you have seen similar kind of plots in previous lectures we have had is that the scatter plot is color coded. Color coded when the people who have got this card have defaulted and not defaulted. And you know what defaulting on a card means. And so we have this historical information that we know. And so we know the ones that have defaulted, will color them brown, and the ones that have not defaulted, we will color them with blue. And so you can encode this and get the plot that you see on the left. This is real data, so something like this. And you can see that when you have the scatter plot, that it looks like quite separated if I'm going to look at just the balance on the card. And that kind of makes sense. So when the balance on the card is really high, these people have incurred lots of things and they have done, then they are defaulting, is what it says. And when it is kind of low, they are not defaulting most of the time. But if you look at the income version of this, or history of the, or part of this story, it is not that clearly separated. There are people who defaulted when their income is high, and there are people who have defaulted while their income is low. And so it's not clearly separated, while on the balance issue it is. This is just the scatter plot, and I just didn't do anything other than telling you what the data is showing. But what you see on the right is something that reveals this more apparently. So we're not doing any classification now. I just wanted to see what we mean by when we're building our way up. But this is also a side story to remind us, for those of us who need a reminder, for box plots. So what you see on the right are called box plots. And we've done this, and we've spent a lot of time talking about EDA and the importance of it. So actually, for this data set, even before we get to having any sophisticated classification algorithm to study it, we actually do get a good sense in terms of having to separate them. Like, for example, balance is a good predictor to classify things. So if I just go do a vertical line and then say 1,500, and now I could be a wizard in that company. So whenever I see people having balance more than 1,500, I will say, oh, these people are going to default, and I'd be right most of the time. And if it is less than 1,500, I could say they will not default, and I will be mostly right? That's the story you would get by looking at that. But it becomes very clear when you look at the box plot, and you know what a box plot is. So you've got the median, which is what the boxes and whatever is written in the middle, and then you've got these things that stick out and out of the boxes that are called hinges, and that take you the variation of this data. And I don't want to spend too much time on it because you already know, but if you don't, then this will be a good time to see. So you've got the 75% quartile and the 25% quartile above and below the median, and then whatever is sticking is the range of it. And if you see any value out of this, you are now safe to call it an outlier. This is what John Taki did when we talked about EDA. In fact, this is one way for you to see outliers, for example. So on the question, so what you see on the left portion of that box plot is when things are still you are doing balance and default. That's the plot you have. And so the balance one is clearly separated, which is what we also saw on the figure, on the scatter plot on the left. On the question of income, it is not, and you can see these box plots not separated from one another in a clear way. All right, so let's continue and see how we can go about doing a classification like this And we have a hammer. We have a hammer that we have learned. We spent 3 lectures on it and a lab session, and that's called linear regression. Can we use linear regression to do a classification of this kind? When we just have now this income and balance thing on a credit card, and we wanted to see whether people have defaulted or not. And you may be tempted to say, why not? Let's consider it. And I want now to be able to say, to turn this, my response now into something that is yes or no, something that is saying, defaulting or not defaulting. And so if I take my y to be a 0 when it's not defaulting and a 1, can we then say, I do this, and if I get a value on my y after I have, did this, model this as a linear regression, if its value gets above 0.5, then I would put it into one of these categories. I would call it default, yes. If it is less than 0.5, I would call it a no. And then that seems like a reasonable thing to do. And so you could begin to think that you could solve this problem using a linear regression. And when your output is binary, which is what we have here, and the values could be 0 and 1, and you modeled it as a linear regression, and you would use 0.5 as a cutoff, which you can think of it as a probability, right? So if this thing is more likely to happen, then I'm going to say default, because the value has become more than 0.5. And if it is less, then it is unlikely, and therefore I will call it no. That kind of makes sense. And for binary, this is not a bad idea. It might actually, that we have a method called linear discriminant analysis. That's just an extension of this that we will discuss not next lecture, but the lecture after that. And so it works. And in fact, you can have you can ground this one better by having a mathematical justification for it, because what we just said about having to formulate this one as a binary value 0 and 1 and using 0.5 as a cutoff could be interpreted as having to find expected values for y when x is a certain value, the expected value for y that is equal to the probability of y being 1, like in this case default, for a given x. Because these two things are equal, then we have a justification for using this linear regression the way we did, and we will be okay. But there is a problem, and that problem is, if we were to, even if it is binary like this, we may end up, because we didn't have any other thing to restrict it by, we just think of it like any other linear regression we would have done, we could have a value that is the y, that is a value bigger than 1, or we could have a value less than 0 because of the numbers that we have had for this credit card, for example, or whatever else that we were looking at. And then we are in trouble, because this whole idea of having to classify them one way or another, the justification for it became meaningful, because we were thinking of it as in terms of probabilities. And if we have a probability bigger than 1, that can't happen. And if we have a probability less than 0, that can't happen. So we need a fix. And that fix is what will bring us to the topic for the day. Part 1 of classification, logistic regression, is what we will do. So we are not far away from regression, and hence the name logistic regression, but we are fixing a problem linear regression would have had if we were think of our problem to be solved in a linear regression fashion, because now we are coming to a situation where probability may be out of a range we would be interested in. We would like the probability to stay between 0 and 1, and linear regression does not give us that ability, and therefore we should stay away from it. So the regression part is kept, but the probability part is going to come as an additional one. So the picture that you see here on the left and on the right is this same credit card information, and we are looking at balance, and what we have on the vertical axis plotted is the probability for default, the way we have modeled it. When we do this in a linear regression fashion, we get the blue curve. The blue curve is our linear regressor, the one that used a 0 and a 1. And you remember the data we had. So it kind of has got more things to say when people have not defaulted, that's 0. And when they have defaulted, it has not been able to say. And there are values below 500, for example, that you can see that the linear regressor for this one was negative. The probability is starting at 0 a little bit higher. It's not just at the bottom. So you can see that it is below 0. So and the brown points are the places where you have people defaulted, right? So when we used a linear regression model for it, the curve that we got was this, and it's not doing a good job for us. The figure that you see on the right, and don't worry how it have come about, does the job we want. First, the probability is bounded between 0 and 1. The blue curve is what we are now getting. This is going to be the one that we are going to use to make our determination whether somebody is going to default or not. And it is going between 0 and 1, just like we wanted it. And it's also going all the way up to the ones that are covered, the defaulted, in a good way. The other one failed. It kind of stopped at 0.2, sort of, maybe a little bit higher. But this other one stuck all the way up. So it covered the range we wanted to cover. It stayed between 0 and 1, and it has exactly what we want to do. That function, as opposed to the linear regression here, is a logistic regression. And we will define it mathematically in our next slide, in a slide or two. But let me give you one more reason to stay away from linear regression. You are already convinced. I am sure you are convinced, and I don't need to spend a lot of time to tell you, if you have a classification problem, linear regression is not the way to do it. That's what I'm building up. But one of the problems that we fixed was that it had the issue about probability. The other issue is this: when it was binary, at least it gave us a chance that it's plausible, right? And at least it showed us some deficiency, and we tried to fix it. But we could also have a situation that's even more severe than that. And this situation is when we have things that are more than binary. You've got 3 things, for example, or 4 things, or 5 things. So for example, when I began, I told you a doctor would like to decide whether a person has got this sickness or that sickness of some kind, right? And in this case, a person comes, and so after some investigation, the physician is going to decide whether the person has stroke, heart attack, or stroke, or it's drug overdose, or it's a seizure of some kind, epileptic seizure. So there are 3 things to choose from, and so we can code this, and we can give them value. The codes that we have seen. The first case is called 1, the second case is called 2, the third case is called 3, and this is fine, right? We've got 3 things, and we gave them numbers 1, 2, 3. And if we were now to continue with our linear regression type of thinking, then we are unintentionally going to rely on some kind of ordering. And so if there is for example, somebody is got 1.8, we could say, okay, this is kind of close to drug overdose than it is to stroke, is what we would say if we were to code it this way. But if you see the difference between epileptic order and drug, it's just 1. Between drug and stroke, it's also 1. That type of numerical value, that ordering, may not be meaningful here, because these 3 things were really different. And so now we have given something that is not a drug overdose, but it is 2.5, for example, had actually nothing to say that this is closer to epileptic. No, it just doesn't mean that. We just had these codes that we were fairly arbitrary, but because we use it as a linear regression model, our model is going to try to impose some kind of ordering to them. And so that will be a bad idea. So just like we had a way to fix the binary classification problem, the default and not default problem, and we had found a way to come around to fix the probability to be in the range we want, and to for it not to be underestimating or not reaching out to others, that kind of shape, we can have it when we have multiple also. And the thing that we would use there is called multi-class logistic regression, or it's also called, or we have also a method called discriminant analysis that we'll be talking about next time. Okay, so now we have made a case. We have made a case for something called logistic regression, and this has got to do with probability. So there are many functions. I'm going to go back for a second. If I were going to say, okay, I need something like this, I want to turn this linear line into a function that stays between these 2 curves, and doesn't go below 0 and doesn't go above 1, but also takes me, both of them are covered. There are many functions I can choose. This is a place where we have choices. We could choose many functions that satisfy this property, and one of them is logistic regression. And that's what we are going to be talking about. In fact, for those of you who are going to be learning or wanting to do project or are really looking forward to deep learning, this sort of things show up there. There are functions that you would choose and you've got choices and things like that. Logistic regression, understanding of it is going to be a good stepping stone for what we will discuss in deep learning there. So just one of the softmax functions that you could use for having to do something like this that has got some desirable properties. So what is it? So we could write the probability for an event or an X for given X when Y is equal to 1. We are going to have a shorthand for the fact that probability of Y, the response variable is 1 given X. We're going to just call it P of X, okay? And this is the probability that we would use for defaulting, for example. So the logistic regression has got this form. There is something on the numerator and there is something on the denominator. The thing on the numerator says E, and this is the number that you know, that you grew up with, the number that we know is the basis for the natural logarithm, right? It's also called Euler's number, and it's got this value 2.78. That's the E I'm talking about here. So that one raised to some expression, and that expression looks familiar, doesn't it? So that is what a linear regression would have been. When you have an intercept and you've got a coefficient for our feature X, the vector X, that's all of it, that exponent of E. So the numerator has got that expression, E to the power of a linear regression looking model. On the denominator, you've got that same thing plus 1. So this whole value now, P of X, the probability, will for sure be less than 1 because I have a number that is something divided by a number 1 plus some other thing. And so it's always going to be less than 1. And this number is going to always be greater than 0 because I'm using a power. E to raise to anything will always be positive. So this has got exactly what I want. And so it is a good candidate. And it has got this name called logistic regression. The reason that it is called logistic regression, if we were in class, I would have written, but I'm not going to write, but I'm going to make you work with me. Suppose you were to take the log of the expression that's written there. So P of X equals to this thing, take the logarithm of the left, take the logarithm of the right. When you take the logarithm of the left, you will get log P of X. And when you take the logarithm of the right, because it is an E and it's being raised to something else, the log of it will be just the exponent, right? So you'll get the beta 0 plus beta 1x pop out when you take the logarithm. And so now if you take things to collect the like terms to the same side, then you will get what you've written on the left now, log of P of X divided by 1 minus P of X is equal to what you see there, beta 0 plus beta 1 times X. Okay, now on the right, we got something that we're very, very familiar with. Just looks like linear regression. We've got an intercept, we've got a slope, we've got an X, and on the left, we have logarithm of a ratio. And that ratio is a probability of something minus or over the probability of the opposite of it, in some sense, 1 minus P of X. This is the reason why I had the horse racing in the introduction slide. This is the reason why I had asked you to tell me what your favorite game is. What you see there in the logarithm is a ratio of odds. So probability of X is you bet the horse that you like to win. That's the probability of it getting it. And 1 minus P of X is the probability of that horse not winning. And so this is this odds ratio. If you were a horse racing fan, if that's your favorite game to watch, you're one of two persons. One, you either really like the sport and the horses and you get very excited and you want, or you're betting. So you want to win money, and so you have got how much money you have put. That ratio is called odds. So probability of something winning or something like that, like the horse, and the other one is losing, 1 minus P of X. And that ratio, when it is big, has got a value. So you take the logarithm of it, and this has got a shorthand name. It's called logit. And what you see on the right is a linear regression, as you probably have needed. This is what logistic regression is. And so we can now come back and see what the previous example I showed you. And this was, it had got this shape. This was exactly a logistic regression. For the credit card example, where beta 0 and beta 1 were calculated using the actual values that were obtained there. Now, this brings me now to just like what we did in linear regression. We had said that, I've got a response variable, and we started off with the simple one where you just have one predictor. We'll say beta was 0 plus beta 1 times X. And if we've got P of them, we'll list them all. And then we learned a method. We learned a method that would be the best fit. And the best fit is the linear least squares, the one that would minimize the sum of the errors that you would make with that line. Much like that, now we were working with probabilities. We have a method that will give us the best parameters, the best beta 0 and the best beta 1 in this case. Now it's not anymore a line, and you're not going to minimize errors because you don't have them. What you have is probabilities. And the method for doing this is called maximum likelihood. And it goes like this. So imagine now you've got a bunch of zeros and ones, a bunch of sequences that have happened that would tell you, and I'm thinking about now one predictor. And you rate a value that was 0, 1, 1, 1, 1, 0, 0, and so on, right? Now, what you really want your parameters to do is make sure that this thing, what you have observed, can be expressed in some mathematical way, and you're going to look for, among all the possibilities, the beta 0 and the beta 1, in this case just beta, that would make whatever it is that you have seen likely event to happen. If that's what has happened, and you wanted to make sure that what you do by using these parameters would give you this, right? The one that you observed is actually what has happened. So what do you want to do? You want to see every time something was a 1, the event has happened, the horse has won, that's P of xi, right? It has happened, that's the probability. The other one is when it has not happened, when it is a 0, and that will be 1 minus P of xi. So each of these things that you have observed now are independent of one another. So you multiply them. When you have events, and you have event 1, event 2, both of them have to happen, then I take, and they're independent, then I take the probabilities of the two things, right? That is how I would get the probability of the new event, or the combination of this. And if I've got many of them, I just keep on multiplying them. So I've got the first term, that is the probabilities of the things that have happened, were true, or probability was 1, yi is 1, and the product of those things that were 0. And so you've got that one. This product, I want my beta 0 and my beta to do a good job by making this one be what has happened in reality, what I have observed. This process, or this method that would give me this parameter, is called the maximum likelihood. That was a likelihood, the L, and the parameters that would give me this are called the maximum likelihood. And there is a person who came up with this one. It's a long time ago. And that person, because I told you about the box plots and who the person was, I will also tell you about this person. This is the person who did that classification about the flowers, if you remember, the petal and wedge and things like that. He's called Fisher. He is the one who came up with this method of maximum likelihood. There is computational issues here. People would always come up with having better algorithms for and so on, but this is the mathematical way to describe it, and it would probably be enough for you to know that. And most of the tools that you would use, you will not need to write your own maximum likelihood finding algorithm or method or something like that. They will be there. So if you invoke them, you will get values. Here is one. Here is one value would get with this credit card data set when we use R to find it. And the function, like linear model, like last time when we were having our code, we called this function called LM. That was linear model. Now we have got something called GLM, and the G there is generalized. And this would give us a logistic regression. And here is the value we got. Now we've got the values for beta 0 and for beta, and the beta 0 is the intercept and the beta is the slope. You've got a coefficient value for 0.005, and you see the p-value for it is pretty significant. So that means our logistic regression could also be assessed in a similar way as we did in linear regression, and here are the values that we got. Okay, now if we get these values, the beta 0 and the beta 1, now we could use now to make predictions on values that are going to come. So for example, if somebody had a balance of 1,000, now we've got a logistic regression model that we have done. This would make you also think about problem 3 in assignment 5, okay? Problem 3 in assignment 5 is about logistic regression, and whatever we cover today should enable you to do it. I know you have started working on the linear regression part because it's already covered, but here is one. So if a person has got a balance of 1,000, you stick in this value with the beta 0 and beta 1 we got, and here we go. So the probability, now we put a hat on it because we are getting it estimated with the parameters we got a value of 0.006. If we say we have a person with a balance of 2,000, and we stick in these numbers, then we get 0.586. And this agrees very much with the kind of figure you saw earlier. If the person is having a 1,000, he's most likely not going to default, or she. And so that is what the probability is telling us. Whereas if we have 2,000, then we have more than half a chance for that person to default, which agrees very much. And so this logistic regression that we just built and the beta 0 and the beta 1 we got are actually telling us something that we could agree with. Now I can, and I'm going to be a little bit faster on this one. And we have 15 minutes, so let me see if anybody's got a question for me. So the last thing I see on chat is football, and football is what Nita likes to watch. Okay, that we know. I'm going to tell you the chat analytics portion of this one later on. But we're working with this credit card data set, right? And you remember there were many variables. Some of them were quantitative and some of them were qualitative. And the income and balance were in fact quantitative ones, but we also know that there was qualitative one. And one of those were whether a person is a student or not. And that one was qualitative. And so in the linear regression model, we had to deal with it being in a dummy variable and so on, right? So we could do exact same thing here, and we are going to now find a value what whether the status of that person is a student is yes or no, and we stick in with the values of beta 0 and beta 1 we got and see what probabilities we would get. And in this case, it looks like being a student or not did not make a whole lot of a difference. I am so happy students are not. I was kind of worried that this data set is going to show that students are likely to default. No, it doesn't look like the data supports that. So you can celebrate as students. When we have multiple variables, just like we have linear regression, where we extended simple linear regression model into multiple ones by having P of them, we could do exact same thing when we do logistic regression. If you have P of them, then the notion of P would be extended in this way. The numerator and the denominator would be extended exactly the same way. Now we have many of them. So for this particular data set, if we include all three predictors, balance, income, and student, where student is actually a qualitative one that says yes and no, we see this, we get these coefficients and we get these p-values. Side note, don't worry about it, but side note, in the example we saw earlier, just a slide ago, we looked at student, we saw them probabilities, and there were some values we got, in fact. Here it is. And we forgot the other predictors and we just focused on student. We got a coefficient of 0.4, the beta, and the p-value for it was significant, right? So this was telling us something and it was significant. Now, when we add it in the presence of these others, balance and income, it is not significant anymore. So the p-value has grown up or grown higher, and the coefficient for it has become negative. This is the place where you see exactly the same type of things that I told you last time when we were talking about linear regression shows up here too. Just because the problem has become classification is not going to change it. Why? Well, this is because there is correlationship between these. These variables are correlated, and these are called confounding. And you probably have heard this term before. Confounding factors. You've got something to say, you know, a patient is has got this disease or that disease, and then you say, oh, there are confounding factors. So we have to look for where they grew up, or we have to see their social status or other things. These are called confounding because they are going to influence what our model is going to say because there is a relationship. And so this example, and I'm going to let you invite you when you do your lunch today, come back to this slide and look at it a little closer because it is a very nice picture. So this is the picture of people who have defaulted and not defaulted. The ones who have defaulted are brown. The ones that have not defaulted are blue. And what you see on the right is the box plot. And you can see the student status, not making it so very clear to separate, but there is a little bit of a difference. But what you see on the left is the default rate, and when it is plotted against balance. When it is plotted against balance, you see there is two different stories that you get. One is the blue curve is higher than the brown curve. The people who have defaulted have higher, I guess, higher, they are higher than the ones who have not defaulted. But when you look at whether they have the student status there, whether the blue and the blue and the brown are student and not student. I have confused this with the picture we were seeing before. So it's student or not student. What you see here is when you are at below a certain income, then the brown curve was higher than the blue curve. When it is above something around 1,500, the blue curve is higher than the brown curve. This one is now teased out because you did logistic regression. And because we saw them in the presence of these other ones, the negative value is coming because of that. So take a look at which is higher and lower, and how the two figures can be read together, and what logistic regression has informed you will be part of your lunch today. Okay, now I'm going to take you to one example because I want to introduce one more concept, and I want to finish the slides I have for today. And this other example is discussed a little bit more in detail in the book, but it's about a study. And I have frequently used this example of about a person being sick or something like that, right? Just like that, this data set, this is an actual study done in the 70s or 80s in South Africa. And the reason this study is featured in the book is because one of the authors is actually somebody who grew up in South Africa, or he's South African citizen. He's in Stanford now, a statistician there. But this study was done about people's intervention about their dietary habits, and the people who were studied there are very heavy meat eaters. So their diet is very heavy on meat. And so the study was about seeing a relationship between heart attack, also called myocardial infarction. That's the medicine name for it. And then they wanted to see, what sort of things could predict that among the samples they could take from their blood and other things that they could do. And so they want to study this and they want to intervene. So here are some statistics about it. The prevalence of this is fairly high because of the diet habit people there have, I told you, is 5.1. And then there were these risk factors that were measured, and the idea was to get a prediction for it. This one is also part of your lunch break today. So you'll go study this one. Is a scatter plot of the 1, 2, 3, 4, 5, 6, 7, or 8 predictors or risk factors that are looked at. So something about their blood pressure, the SPP, there is some kind of blood pressure, whether the person smokes or not. Tobacco use is another one, and it goes on the good cholesterol and the bad cholesterol, and the age of the person is all there. And so in this scatter plot, what you see with the brown color is people who have got heart attack, myocardial infarction, and what you see in blue is people who do not have. And this is a study made on 100, some number that I showed you earlier. When people who have it, these are called the cases, and the controls, people who are not have it, and you are going to study them. So here is a scatter plot, and you can see some correlation in some cases. The tobacco one is an obvious one. When people are users, they have higher tendency of being RAID, which is, they have the heart attack, and the other ones do not. The other ones are probably not so clear. And there is family history, which is what you see on the 1, 2, 3, 4th one. And you can see whether the person has got a family history of heart attack or not is what you see, and it looks like having a family history contributes to this. So you see relationships like this, and here is what the logistic regression model on it showed. So there is some numbers to look at here, and we have time, so I'm going to walk you through or show you, point out a few things while this is displayed. So the first thing to show, this is code, this is R, is what method is used to get the logistic regression model. And I have introduced this one before. It's called GLM, the generalized linear model. And the generalized linear model has got very many other things. It's not just logistic regression, but there are many other things. The thing that actually makes it logistic regression is this parameter called family, and that family is not the family history. This is a function called, this is R, and it's called binomial. When you use binomial, you're using the generalized linear model, GLM, and you call it with this parameter family equal to binomial. Now you're logistic regression. So this whole thing now is logistic regression, is what it means. I'm telling you now, I'm reading this from right to left, like Arabic, right? So I started with the parameter at the very end, but the GLM is the function called, and now you are going to tell it what the response variable is, and this is whether somebody has got that disease, heart attack, and that variable is called CHD. And as a predictor, we're going to use everything. That's what the tilde dot means. And the data set for this one is the thing that's called heart, okay? So now we know how to read that line. So we've got logistic regression, and we see a summary. This is what we did for linear model also, for this model that we just fitted, and it's called heart fit. And we see the information we got. We've had these predictors, and we see what contributions they make by looking at their p-values, and some of them are very significant, like SBP, like tobacco, like family history, and there are some that are not very much related. And so you get these values, and you get some other additional information about what this one is showing you. This is going to take a little bit of time for me to explain to you. And this whole thing, what I just told you about having to look at, intervention studies of this kind is called case control study in epidemiology. I'm not an epidemiologist, but have read enough, and on another course we actually talk about epidemic models and things like that. But in epidemiology, in public health, you have this thing that's very frequently used, case and control. And there are some statistics students in the class that would correct me if I'm saying something wrong. But case and control is a way to do studies that would have costed you a whole lot of money and would have taken you a long time if you were to study it in a different way. What would be the different way? These people were looking at these people living in South Africa, and they were studying their relationship between these risk factors and heart attack, and they picked 160 cases and 322 controls. The 116 cases are the ones that are heart attack, and the 302 are the ones that are controlled, that they're going to study them. If they did not do it this way, what they could have done is watch these people, look at them for 30 years, record their things, see whether they are going to get heart attack or not. After 30 years of study, you would have done that. And you could say, okay, we've studied these people, we've followed them for all these years, we've logged their life and what they ate and what things that they have, and here is the relationship between the risk factors and this heart attack. That's obviously very, very costly. You're not going to live for a study for 30 years and report something after that. You probably won't be around, and so instead of that, you would take people that have the cases. These are the cases. People, and then you have got the controls, and then you model them using the kind of things that I told you with this study that you have. But the prevalence in this particular case was high. That area was high in heart attack. And the cases and the things that you have after you get a model would give you something that probably is not going to reflect what in reality the prevalence of the disease was. And for that, you could account for, and you could do mathematically correct it. And this is what the purpose of this slide is, to show you how you can account for it to change the intercept, not the slope. The slope is fine, but the intercept could be changed by looking at what the prevalence was, something that and that would depend on the number of cases you looked at for your case control study. And that formula is right there. If you really, really are curious, you can look into how it came about, but you have a way to correct it. Let me finish off with this slide. And I have a couple minutes. I have succeeded in getting through my slides. I'm not sure if it was so clear, but I have gotten through my slides. This will be the last one. So I just gave you very roughly why you would want to do a case control study in epidemiology. But it's not only in epidemiology that you do case control study. You actually do it very many times. In fact, you do this thing when you have unbalanced data sets, which you will encounter all the time. So for example, you work for Google or Amazon, and they want you to look at CHD means the heart attack. I don't remember exactly what CHD stands for, but it is the one that you actually wanted to predict. The book has got an explanation for it, Chris. You are working for this company, and they want you to look at how many people clicked on an ad. and then they want you to count it, and then won't tell you. They are not, many people are not going to click on ads. There are very few people who would do. So if you look at the logs and somebody has clicked or not clicked, clicked or not clicked, you will have so very many not clicked ones compared to clicked ones. And if you were to do some model and you're going to come up with some cool algorithms for them to do a recommender system, then you have a very unbalanced data set to do click or no click, right? Click-through rates. What you would do instead is to find out how many cases and controls you would need to make a study. And this plot shows you that, the ratio between control and case. And as you can see, and the return how you have on your ratio is what you have on the vertical axis plotted. You can see that after a ratio of 6:1 or so, you don't get a whole lot of benefit. So that now you've got an answer, how many case to control numbers you would need for your model to be a reliable one. You can read about this one a little bit in the book. I think it has got at least a page-long kind of discussion, but this is all I wanted to say. Diminishing return is it's called, and it shows up in very many other occasions also, where you kind of get a diminishing return to whatever it is that you are trying to investigate. But case control is important, was my point. Okay. I have to stop here because it's become 10. Let me see if anybody's got any quick question for me. This is my last slide. You may read in the book, go over the slides one more time, and we'll continue discussing classification next time. And next time, we're going to look at something called k-nearest neighbors, a very famous algorithm. The book does not do a good job, so I'm going to use my own thing to discuss that on Wednesday.